All right. So yesterday we started talking about intermolecular forces and polar covalent, not polar covalent bonds, but different types of intermolecular forces like London forces, like dipole interactions, like hydrogen bonding, and then ionic bonds. And today we're going to extend that, and we're going to talk about a couple of things. And we're going to start with a little bit of a warm-up to see where we are with these functional groups, because this is, again, your functional groups determine a lot of your physical properties, right? So they're going to help determine like what the boiling point of something is, or what the melting point is, or whether it can hydrogen bond, or whether it can, whether it has dipole interactions, and so on and so forth. So with that being said, let's go through and see how quickly we can do this, since we've already been exposed to functional groups before. This is phenacetin. It's the precursor to this, which is acetaminophen. Right? What are the major functional groups present here? Anybody?
Aromatic.
Aromatic. Okay, good. I'm with you. What else?
And alcohol.
Good. Got an alcohol right here.
Is that a ketone?
Well, there's a carbonyl there, but what's bonded to it? It will be a ketone.
Oh, it's bonded to a nitrogen.
Yes, good. So what is it? That nitrogen changes the whole complexion. It changes the functional group identity. Whatever. See, carbonyls are kind of a common functional group until you start attaching stuff to the carbonyl carbon, which is, in this case, would be right here, this carbon right here. What is it if there's a nitrogen attached there?
Amide.
Good, amide. All right, good. All right, what about, so we know we've done this. What about here? What did we do to this alcohol? What is it now? And let me fix that, because that looks kind of grainy. But modern technology, we can fix that. All right, what functional group is that hanging off of that ring now? Right, you have an oxygen, and I'm saying suspended. It's not really suspended, but it's between a carbon on this side and a carbon on that side.
Ether.
It's an ether. Excellent. Oh, we already did the rest of them, so we're not going to go back through that. What about here? Here.
The one at the top is an acid.
Okay, good. Carboxylic acid. What about on the bottom? See, they both have C double bond O. They both have that motif. You can see it right here. But what's on the O matters. If it's a hydrogen, then it's a carboxylic acid. If it's a carbon, which in this case, that oxygen is bonded to a carbon, what is it now?
Anhydride.
Ooh, good. Okay, so you're in the ballpark, because an anhydride is a type of one of these functional groups. But this, an anhydride would look like this. It would be it would look like that. But it's still this type of functional group though.
Ester.
It's an ester. And hydride is also an ester. That's good though. All right, let's go to, I think we've done this one already. This is THC. We've done that one already. But for practice, let's do it again. What is this group here? What do we call that?
Alkyl.
Good. And here. Look at the structure. An oxygen, you got a carbon on the left and a carbon on the right.
Ether.
It's an ether. Good. All right. So now we're going to kind of shift gears and we're going to talk about, well, we can work through this. I should have pushed this up when we were talking about polar covalent bonds, but it's okay. You can never have enough practice. This is a good warm up. So the question asked to look up the electronegativity value. So you can just pull up a periodic table with those values on it. And let's work through these real quick, see if they're covalent, or non-polar covalent, or polar covalent. And remember we said, what was it, 0, 0.3, and then was it, oh, it was 0.5, wasn't it? So this is non-polar covalent, this is polar covalent, and this is ionic. I think those were the values we used. All right, what do you think? What is the electronegativity of fluorine? And we know carbon is going to be 2.5, so we're going to have to keep looking that up. What about fluorine?
It says 3.98.
We're going to round it up to 4, if that's okay. How do we tell how do we calculate this difference? So the difference in electronegativity, we're just going to subtract that, right? So it'll be 1.5. Where does that fall on the scale?
Polar covalent.
Polar covalent. Let me move this over. All right. What about here? Carbon is 2.5, and then oxygen is 3.5. Where does that fall?
Polar covalent.
It's also polar covalent. And this carbonyl is highly polarized. And when you think about it, what we know about resonance, the fact that you can take that pi bond and give those electrons to oxygen and create a full positive charge on carbon, that matters, right? This is a highly polarized bond. All right, what about here? Silicon and carbon. It's the silicon carbon bond right here. What's the electronegativity for silicon?
1.8.
So that's 2.5 minus 1.8, but 0.7. So that also would fall into that category of polar covalent. Is that right? It's from 0.6 to 1.5. We'll say that's also polar covalent. All right, last one. What about this one? What's the electronegativity of chlorine and bromine? I think bromine is 2.8. Is that right?
Yes, and chlorine is 3.0.
So this would be 0.2. So obviously it falls between the range of 0 and 0.5. So we can say that this is non-polar covalent. Questions about that? Right? For the polarity, again, we just use the scale. 0.6 to 1.5 is polar covalent, and 0 to 0.5 is non-polar covalent. All right, I think let's do this next question. It says, which will display a dipole, a molecular dipole, show the direction of atomic dipoles and the molecular dipole if it exists. So for this structure on the left, we know that a carbon fluorine bond is going to have a dipole in which direction?
Towards the fluorine.
What's the fluorine? Good. Here and here, right? So do you think those two vectors, let me fix that. That looks so sloppy. Do you think those two vectors are going to add together, or do you think they're going to be destructive towards one another? Right, look at the general direction. Aren't they both going in the same general direction? So the overall dipole or the molecular dipole, we could say it's kind of like that, yeah? Uh-oh. Is that right? Because remember, a dipole,
Yes, that's correct.
yeah, a dipole is a vector. So it has magnitude as well as direction. What about over here? We know that the bond is going to be polarized towards fluorine.
They would cancel each other out, right? Because they're going opposite directions.
They're going to cancel. That was a question on the test about which molecule would display a dipole, and I gave you the condensed form, and you know what is helpful in that case to write it out, like in the case of, I think it was CH2F2. I think that was one of them. When you have a halogen, like a halogen, because it's so electron dense, like it has like 3 long pairs around it, that halogen, those halogens are not going to be, they'll never be on the same side, like unless it's impossible, like a structure like this, right? But over here, when you write it out, right, it's the best practice is to put the halogens apart, because if you put them together, then you're going to have a lot of electron repulsion, like if I put them on the same side, right, you're going to get a lot of electron repulsion between those two atoms. Right, and if you write it like that without kind of understanding the electrons and how they are repelling one another, then it might be tempting to say that there'll be a dipole, but the understanding is that the fluorines are going to be on opposite sides of one another because of the lone pairs and the electron pair repulsion. All right, so with that being said, all of these functional groups have, they bring different characteristics to a particular molecule. So when we think about these intermolecular forces, those intermolecular forces are going to be dictated by functional groups. They're going to be dictated by what functional groups are present. So in this case, it's asking now, it says rank in order of increase in boiling point. So I'm going to we're going to drill down on that a little bit. And it says indicate which intermolecular forces are present. So when you have a situation like this, where you have all alkyl chains, right? Alkyl chains and carbon hydrogen bonds are not highly polarized. And so in this case, again, we said this on Wednesday, right? Every molecule experiences London forces. How many of you watched the video that I sent? At least one of them. I know I sent one about solubility as well. But so van der Waals forces, let me kind of explain that a little bit. And I think in the video, I likened it to Velcro. Right, so you have all these carbon hydrogen bonds. Right, and within these carbon hydrogen bonds, you have micro dipoles. They're not huge dipoles, but carbon is more electronegative than hydrogen. So this is going to be partially negative, and then the hydrogens are going to be partially positive. And that's all the way through this whole molecule. So this is partially positive, partially negative. Right, and so if you have another one of these molecules that's in the vicinity, let's copy it. Right, you can imagine with all these little micro dipoles that the positives are going to seek out the negatives and the negatives are going to seek out the positives, right? So with that being said, that's what holds these molecules together. That's what causes them to pack, right? The attraction between the different charges. I liken it to Velcro, right? If you're going to pack these molecules together, it's like packing Velcro. So you'll have an array of these molecules packed together. And what's holding them together is the charge, those little micro charges. Micro dipoles. So that's how, kind of in a nutshell, how these van der Waals forces work. Right, you got all these little micro dipoles, and they are seeking each other out. The positives are looking for the negatives are looking for the positives, and so they just kind of and actually that was a paper published, because I know we talked about the strength and saying van der Waals is the weakest out of all of them, but there was a paper published. I need to find that. I think I downloaded it. There's a paper published that kind of refutes the weakness of the van der Waals forces, saying that they're stronger than we think. But I'll find that, and maybe I'll share it with you. It's actually a really cool publication. So what that means is that when we think about boiling point and melting point and things like that, the stronger the intermolecular force, right, the harder it is to pull those molecules apart and get them, in the case of boiling, right, you turn them from a liquid to a gas, but you have to first disrupt the molecule itself, right, or the order, right? If you have a stack of alkanes like this, in order to get them to boil, right, you got to break them up. Before they go from liquid to gas, the molecules themselves have to be broken apart. Right, you got to put some space between them so that they can become a gas. Because remember, in a gas, your molecules are much further apart than they are in a liquid or a solid. Solid, they're the closest they can be. And then in a liquid, they're a little further apart. And then in a gas, they are all over the place, right? But in order to get something to boil, you have to, again, agitate the molecules, push them apart from one another so that they get converted into a gas. So with van der Waals forces, what you have to think about is how well a molecule packs together, right? That's when we're talking about boiling point and melting point and physical properties. For the boiling point, we want to think about how well these things pack together. And we want to think about surface area. So those two things kind of go hand in hand, right? If it's well packed and you have a lot of touch points along the chain, that's going to increase the surface area as far as like those micro dipoles are concerned, and it's going to make it harder to pull those molecules apart. If they're not well packed, that means the surface area and the touch points are lessened, and so it's going to decrease the boiling point. So well packed implies increased surface area. Come on, Russell. Right, so you got more touch points, more places where those little micro dipoles can line up and be attracted to one another. And if that's the case, then it's going to change the physical properties. So all of these molecules up top experience van der Waals forces. The question is, which one is going to boil faster? What that means is which one is going to be less well packed, which one is going to have the least number of touch points, and which one is going to be less ordered. So let's do this. I want to do it in reverse. Somebody look up the boiling point for, let me see, 1, 2, 3, 4, 5, 6, 7, 8 octane. And then while you add it, somebody look up the boiling point for 2, 3, 4, 6. 2, 3, 4, 6 tetra methyl octane. And then somebody look up the boiling point for 3,4-dimethyl octane. And based on that data, we're going to compare the boiling points, and we're going to use that to explain why one is higher than the other or lower than the other, so on and so forth. Anybody got this one yet? Octane, the boiling point.
Two hundred and 258.1.
You said 250,
258.
258, that Fahrenheit or Celsius?
Fahrenheit.
Okay, all right. So all the other ones need to be in Fahrenheit also. So 258 Fahrenheit. Trying to calculate that. 596 plus 32. All right. What about the next one? 2, 3, 4, 6 tetramethyl octane. And then what about the last one? Anybody got the last one? Molecular weight, structure. Okay, I think I found it. Come on.
For the 3,4 dimethyl octane, I got 325.4 degrees Fahrenheit.
Okay. And what about the middle one? Where'd you find that boiling point? Because everything I'm pulling up, none of it has the boiling point. Sucks.
It's on a website called CHEM Spider.
CHEM Spider. I saw that. me see. Okay, okay, yeah, 163 Celsius. That's 325 Fahrenheit. All right, what about the middle one? Let me see if I can find that one. Come on. I don't see this one. And this is computed properly. This may not exist. Let's try something else. Well, actually, let's compare these two. So this boils at, so let's look at the first two. So octane and 3,4-dimethyl octane. Octane boils at 258, and then 3,4-dimethyl octane boils at 325, right? What's the difference in those two? Normally, when you have branching like that, it actually disorders the molecule and makes it puts more space in between the molecules and makes it easier to agitate and easier to get into the gas phase. But in this case, we don't see that. So what do you think happens between octane and 3,4-dimethyl octane? What's the difference?
The methyl group. I mean, like the branches and stuff.
Yeah, you're right. You called it right. The methyl groups here and here. So if the boiling point is higher for that 3,4-dimethyl octane, what that means is that it packs better. And there may be some symmetry there with those two methyl groups, because in order for the boiling point to be increased, you have to have a higher surface area and better packing between the molecules in solution, right? So again, I want you to think about this in terms of having a beaker, right? And a beaker full of, let me just cut this and paste it. A beaker full of this, right? Right, so you have multiple molecules of the same thing in a beaker, and what you're trying to do, if you're boiling this, you want to get it to, right, get those molecules apart from one another. So the way we can explain that is that we can say that the surface area is increased compared to octane, right? And again, a methyl group is a functional group, and the presence of those functional groups changes the physical properties of 3,4-dimethyl octane relative to the octane itself, which is unbranched, right? Just an 8-carbon chain. I wish I could find the boiling point for that other one. Let me see. I'm gonna try to take off one of the methyl groups and see if I can find that. Let's try methyl. Doesn't have a boiling point on here. This sucks. Kind of really threw a monkey wrench. And hold up. Okay, so the boiling point here, let's do this. We're going to take off one of the methyl groups. That'll be adaptable. I'm going to take this one off. So 2, 3, 4. Let's calculate, or let's compare that to the other two. And the boiling point I have is 180 degrees Celsius. So we need to convert that to Fahrenheit. So 356. What can you, so now if we compare that to the second one, or to the third one, what do you think? Because the boiling point actually went up, didn't it? It's 325 for 3,4-dimethyl octane and 356 for 2,3,4 trimethyl octane. How can we explain that?
It has another methyl group added
Another
to the
methyl
chain.
added, yep. And so that and because of how orderly it is, it probably packs a little bit better even than the 3,4 dimethyl. So you increase the surface area, you increase the number of touch points, and you increase the boiling point. Anytime you increase the surface area with those van der Waals interactions, that's what the strength of those interactions is based on. How well the molecule packs and where the touch points are. So even with this, it's probably the increase in boiling points probably due to surface area increase. Right? But normally when you have branching like that, it actually drives the boiling point down again because the branched substituents push those molecules apart in solution and makes them easier to agitate. But in this case, that's not the case because of the order. Because if it's orderly, it's going to pack better. And if it packs better, then it's going to be harder to agitate and get into the gas phase, if that makes sense. So let me put that down here. All right. Let's look at the next example. And it says rank the following in order of decreasing melting point. So melting point, boiling point, physical property wise, you're going from a solid to a liquid, but the idea of surface area and what type of intermolecular force is present matters. So all of these have a dipole present. Right, so in addition to having, remember everything has van der Waals, so you can say that for everything. But in addition, you also have dipole interactions. right? And if we had to think about the dipole interactions, it's similar to van der Waals, but the difference is that you got actual charges that are much higher. So let's take that first one, the ketone. Right, you actually have polarized bonds that are present. So this is partially negative, that's partially positive. And then the next one that comes is going to be aligned in such a way that the negatives and the positives find each other. This is partially positive, that's partially negative. Same thing here. Partially positive, partially negative. And so when you have dipole interactions, that's a little bit stronger than van der Waals traditionally, because the charges are greater, right? These are not micro dipoles, these are actual polarized bonds, right? So you would have a dipole for each one of these. And again, it's really tempting to think about these molecules in isolation, but we're talking about having a beaker full of these molecules, right? And they all just kind of coexist together, right? So all of them have dipoles. What do you think is going to determine the difference in the melting point? Again, surface area matters, packing matters, but now we're talking about these dipole interactions. What do you think is going to hold these molecules together? The other one was an alcohol, wasn't it? I don't know if I got enough carbons, but fix my beaker. All right. And then what was the other one? Fluorine. I don't remember where it was, but it doesn't matter. All right. All right, so there's a dipole here. Oh, backwards. This is partially negative. That's partially positive. Partially negative. All right, so those dipoles are all going, again, they're going to line up and find each other. Now, there's something going on with the alcohol that the other two can't do. All right, so this is dipole, this is dipole. The alcohol has, of course, a dipole going in this direction. But there's also another force that's possible here. Right? So this is dipole, but the OH group introduces another intermolecular force that's possible, right? And that is hydrogen bonding. Right, and again, that's the strongest of all your intermolecular forces. The way that works is if I have one of these alcohols like this, right, the lone pair on another alcohol in solution, in the same solution, is going to be attracted to, let me switch pins. That lone pair is going to be attracted to that hydrogen. Because that hydrogen, again, is partially positive, and then the oxygen is partially negative. And that interaction by itself is really, really, really strong. So that lone pair is going to have an attraction like so, right? And all your alcohols are going to do that. So if you had to, without knowing the boiling point, if you had to determine or estimate which one is going to have a higher melting point, which one will have a higher melting point or take more energy to pull apart to go from a solid to a liquid, which one would you pick?
The one with the hydrogen bonding.
This one. Yep. Because the way, again, your physical properties are affected by what intermolecular forces are present. So if you have both dipole and hydrogen bonding, then more than likely that alcohol is going to have your highest boiling point. And then if you had to compare to others, how would you compare those? What would you do? They both have dipoles. Which one, how could you tell which one has the strongest dipole?
It would be like probably which one's the more electronegative or something, right?
Excellent. Excellent. You can compare the difference in electronegativities, couldn't you? And determine which one of those is more polar. And then by that, you can tell which one would have the strongest dipole attraction. So you can compare the difference in electronegativity. All right, we got to stop. I'm 3 minutes over, unless there are questions.